So far, so good. And sync this guy up. Oop. Everything's working. One of the reasons, or one of the underlying principles of linear regression, it is that what we do is we look at the slopes. And similar to when we looked at the mews or the means, and we said, okay, which one of these is not like the other? Are they the same or are they different? In linear regression, we're actually going to look at the slope, and the is there a difference in the slope or not is going to be your null in the they are the same, and your alternate in that they are different. And one of the underlying principles here, and like I said, this is the reason we do ANOVA first, is that if the variances are the same, okay, then much like we made the inference over into the means, we can now make that same inference or that same connection over into a line. And you've done algebra, right? Everybody's done algebra? Everybody's taken algebra? Everybody's taken calculus. Calculus is based on linearity for sure, okay, and continuity, okay? And what is the definition of any line? The mathematical definition for any line. Yeah, and it's the shortest one, right? Yes, it is the distance from one point to another. In some respects, yes. Okay, I'm looking for y is equal to mx plus b, right? Right? Okay, and m is the slope. And you said b is the other one, mx plus b, okay, and b is the y-intercept. Now here we're going, and the purists would say everybody should do mx plus b, or everybody should follow that, but the text, and many people kind of create their own sort of coding. And so what I'm going to do here is I'm going to sync up with what's in your textbook. So instead of mx plus b, I'm going to go b sub 0 and b sub 1. All right, and I'll show you what I mean by that. Okay, so yes, that's it. Y is equal to mx plus b. The slope times the value you have for x plus b, and you can create, and all you're doing there is you're creating the best fitting line for all your data points. All those dots that are on you remember the scatter chart you did? All those dots, okay, represent a data point that can define a line, and you create a line that best fits. And then if you can create that line that best fits, you can now discern and interpret what that information is telling you, much like you've done with t-testing, much like you've done with ANOVA, and much like you did with z-testing, okay? Much like you did with variance analysis. It's telling you something. That information is telling you something, and that is, again, one of the big takeaways from this is being able to do the mathematics is interesting, for sure, and it's important. But the computer, the software, is going to do that for you, and so we will move very quickly from the theory I'll talk about today, and then we'll move into, okay, let's run this through Minitab, and what's Minitab telling us? And how do we create that definition of the line, and how do you know that line is significant? Or the slopes are the same or different? What are you going to look for? What do we always look for? The p-value, that's right. Yep. When in doubt, look for the p-value. And when in doubt in this course, always assume normalcy of distribution. So we're going to talk about simple linear regression models, x and y. We're going to have an independent variable x that is on the x-axis, and we're going to have a dependent variable y that is on the y-axis. It's very, very simple. And we're going to take any set of data and determine whether or not there is a relationship between x and y based upon the slope of the line. Okay? Anybody been skiing? Snow skiing, not water skiing. Water skiing. How about snow skiing? Snow skiing. Snow skiing. Okay, and you look down, and what do you see on the hill? What is that? What would that be called? The slope, right? Okay, I'm overleading it. All right. Now, if you're on water and you're skiing, what kind of what kind of slope do you have? This is a brand new metaphor I'm trying. You have no slope, right? It's just straight across. Right? Ooh, yeah. Yeah, but that's sinusoidal. Yeah. And it's a grammar sort of thing too, you know. I mean, that's good. I have to remember that. That's grammar. I actually always go blame it on the computer. Oh, the computer, computer screwed up again, you know. What is it? Auto. Oh yeah, auto. Yeah. All right. So, and we're going to use the least squares method, and all that means is we're going to find, based upon the least squares, we're going to minimize the error that this line represents as far as its relationship to all the data within that data set. That's all we're going to do here. And then this coefficient of determination, this is really, I think this is actually more important than linear regression in some respects, because we actually go in and the coefficient of determination is all you're doing is squaring up the correlation value. And once you square up the correlation value, I can say within 95% confidence level that sales is accounted for by 34% of how many salespeople you have, or how much advertising you have. Or I can say 40% of our manufacturing abilities are based upon how many people we have. Well, and some of these might seem really basic, but as we've talked before, there's always that golden nugget, okay, that you go, wow, I didn't even know that was going on, because you'll see that in the data, okay. And then we're also going to test for significance. Every time we're going to go out, our standard significance value is, what's our normal alpha or sig level? What's that? P.05, P.05 every time. Boom. Unless you see something different, it's always going to go P.05. I think I talked about most of this already. The managerial decision, because you're trying to understand those relationships. Here we go. All right. We already talked about this. Dependent and good. All right. Talked about that. Multiple regression. All we're going to do here to start out, we're going to start out with single variate, and then you might hear a term univariate analysis. Univariate just means we're working with one variate, or more plainly, or more pointedly, variable. One variable, univariate. Multivariate is two variable. Multi-regression is two or more variable. Okay, multivariate is also two or more. Just to make sure that just to kind of do away with all the potential language differential that's going on here. Okay. And we're going to create these regression models, and here is the magic formula. So y is the same, okay, except the intercept we're going to call beta sub 0. This is a beta, and you'll see this as when we get into, and this is for a population, and when we get into samples, you're going to see B sub 0. So what you saw before, what you learned in algebra, still applies. It's just that here in this textbook, for whatever reason, we're going to use beta sub 0 to represent the y-intercept. And then, instead of m, okay, m times x, as you learned from, I don't know, you probably learned that in 7th grade, y is equal to a plus mx, right? M is now b sub 1. Now the more interestingly, is this is a little bit different than what you're used to, is that there's always some error. You can virtually, I'm going to qualify just a little bit. You can virtually never draw a line or create the definition of a line and never have something that is not exact as far as fitting all the data. Something's always not correct, and that's error. And this is an epsilon. Okay. So anytime, and you'll see this, I'll kind of drive this home a little bit in both the quizzes and the exam for sure, is that you're never perfect. And that's why we always run these at p.05. But the lower your p-value on your testing, so for example, if you got a p.05 versus a p.01, you're going to get less error at p.01. p.02, you're going to get more error than p.01. And if you see an error in some respects also drives your test statistic. And what we're doing when we say y is equal to beta sub 0 plus beta sub 1 times x is we're saying that it's a regression equation in which you can now take any value of y, any value, and you can determine, or any value of x, and you can determine what the value is going to be of y. And this is an expected value because there's always some error. So when you take this error off over here, you have to move this to an expected, kind of an expected sort of nomenclature. Good enough? B sub 1 is the slope, and the slope is just if you're looking at the top of a mountain and you look down, what do you see? You see a slope, right? If you're at the bottom of the hill and you're looking up, you see a slope. Now, is the slope positive or negative? That's going to be important as well because remember we talked about whether there's a positive or negative correlation between two numbers. Are they directly correlated or directly proportional, or are they inversely proportional? If you have a negative number, are you going to have a negative slope or a positive slope? If you have a negative slope, okay, are you going to have a negative beta or a positive beta? I'll say it a little bit differently. You're going to have a negative beta, right? And the slope is going to have a negative slope, and I'll show you what those look like. And it goes to whether it's a direct or positive relationship or a negative relationship. And that's why it's important to know which type of slope or which type of correlation you're looking at. And one of the reasons is that you square it up because you always get a positive number when you go to coefficient of determination. Here's a positive. And here's a positive. It slopes up. This might be a nice way to think of it. Up. All right. You bet. You can actually have B sub 0. You can have a negative y-intercept and still have a positive slope very easily, very, very easily. This might not be a important variable. So, for example, sometimes if you're looking at how much money people contribute, and that'll be one of the first cases, how much money people contribute to a specific cause. That thing's supposed to stand still after I click it. Yeah. I'll stop moving my hand around so much. Oh, there it goes. No, it doesn't. Okay. Yeah. So can you have negative giving? Okay. Actually, you can. Let's say been to church, or you've donated to a cause, and they metaphorically or physically pass the basket around. Okay. Can you have negative giving? No, unless some guy sticks his hand in the basket and pulls it out, then you got some negative giving. But for the most part, you've always got a positive giving. But you might have a y-intercept in that specific situation that's down here, but you still have a positive slope because the more people you have at church, or the more people you have giving to your cause or potentially giving to your cause, you're going to have a positive relationship. And so we call beta sub 1 positive, and it's a regression line. And here's your x, and here's your y. And when you draw this line, and you get all these dots, all these data points out here, there's always going to be some error, and that's why you either use expected value of y, or you make sure you put in there something that epsilon at the end recognize that you have some error in any relationship as far as understanding the exact relationship and by formula. There's a negative slope. The slope's down. So you're at the bottom of the hill and you're looking up. Or at the bottom of the, or you're top of the hill and looking down. So the way, I don't know, it's kind of hard to remember this every once in a while, but just remember that this is down. That's the way I kind of think of it, down. And this is up, so positive, down. And you could you have a you could have a negative slope as long as you have a negative data set on the y. Yeah. So it could drop down in this area as well. And that's a negative linear relationship. Okay. And other than the grammar error, okay, I don't mean to keep it, that was really going, I have to use that one. Other than the grammar error, a lake is a good metaphor. It's a straight line. There's no relationship. Okay. That means that your, if you have no relationship, what would your R value be based upon what you learned in BANA 1, or maybe I think even we covered it a little bit in the intro part of this BANA 2. What would the R value be? What would the correlation coefficient be for this line? Yeah, that's right. It's 0. Exactly. Okay. And if you square 0, what do you get?
0.
You get 0 every time. And so basically you're saying there's no relationship, there's no correlation. Here you can begin using correlation, but you're going to actually have, it's called a Pearson R, and there's a couple others in there, but you're going to have a Pearson R, and the R value on this is 0. You square up 0, and you can now say that the value, the value of x accounts for 0% of the y outcome. Now, just like we did in ANOVA, just like you did in t-testing, just like you did in z-testing, in order to find out in order to understand the relationship and whether there is a slope which would indicate whether there's a strong or negative or positive relationship, do you have to sample all 1.2, well, let's not pick on we did the Chinese, we did the India, Pakistan. Do you have to go out and talk to all 400 million, if I've got it right, 400 million people in Pakistan to figure out how the Pakistanis as a population or as a culture feels about the United States? No. I'm sorry?
No way.
There's no way. It would be dangerous, and especially in the was it the Punjab, was it? No, careful, that's religion. There's a province where all the gangsters hang out. All right. So yes, it would be dangerous, but you would have, in order to find out what all Pakistanis thought, someone's going to have to go out there and talk to those in that specific province. Okay. So we create a point estimator. So instead of going out and talking to all 400 million people, all 10,000 customers, we create a sample. And generally, we've decided, again, a heuristic, a general guideline, is that about 30 is the right number for a sample size. And then from there, you can vary it up based upon how large your population is. Okay? So if you're wanting to find out what 100 million people think, how many people would you have to sample theoretically? Something over 30, for sure. Okay. But, however, when you get to about 1,200 or 1,300, it's a point of diminishing returns, and for even 5 billion people, right? You only need to talk to about 1,400 of the population, 1,400 of the population, in order to get this estimate of what the population thinks, and you do that by going with a confidence level. Yes, sir.
So like, how many do they ask per state when their election time comes up? How do you know how much they have sampled?
Yeah. They will sample it. It's not a big number. This is on a presidential election or something like that. Yeah, it's not a big number. It's about sometimes you see 1,200, sometimes you see 1,400. But the key there is that they do a geographic, or they stratify or do a segmentation, and so they'll actually go out and make sure that they have representation from every county, in most every county, and there are 10,000 of them in the country. Now, do they have to go to all 10,000 counties? No. But you have to make sure that you don't pick, that your random selection doesn't have 500 people from North Dakota in it. Because then you get an oversampling of the people in North Dakota, and that would create error, which is also, by the way, also in the general category of invalidity. Good question. Thank you, Anthony. It's Anthony, right? Yeah. All right. I'm clicking it. So here's that estimation process. This should look a little bit familiar, and that's why I put this chart up instead of what was actually in the text. And this should look very, very familiar. All we're doing is a point estimate of what the population is saying, okay? Or what the population would say if you talk to all 100 million or all 10,000. And so we have here, click one more time, come on. There we go. Sometimes it's slow. So I wonder if my battery's getting low. Okay, so you have this, here's your regression model for the overall population. You pick your sample data, or you select samples. Okay? When you're writing it, you select. When you say it, you can say picked. All right, and then you come down here, and here is the equation. Now you'll actually see this is a y hat, this little umlaut, it's not even an umlaut looking thing, this sideways greater than sign is this called y hat. So you'll say y hat is equal to b sub 0 plus b sub 1 times x. And that's how you will create a point estimate for the overall population. And so you are now saying that b sub 0 as a point estimate of the sample is the same as beta sub 0, and b sub 1 is the same as beta sub 1. Beta sub 1 is the population. Remember how we talked about sigma versus x? Same thing. S, the letter S was the sample population, or the sample standard deviation, and it was the point estimate for the standard deviation of the overall population of all 100 million, as opposed to just a sample. So we apply this least squares criterion, and that's what you're really doing when you're doing y is equal to, when you did the y is equal to a plus mx, you're creating a line that best fits the data, the observed values. That gives, this is the equation, that's exactly right, and that's why they call it least squares, because it's the least squares of the error. So you minimize the error. Thank you, Mitch. Good. And so here's how you determine the slope. And it's a minimization of the error. You pick a slope, or you actually calculate a slope that best fits the data. And then you go out and you pick a y, and then you pick a y-intercept that best fits the data, and that creates a line or an estimate if you are doing a sample. And you can put means in here too, by the way. So you can group means. You can do a grouped mean, so you can have 10 situations, or like you had the states. You could create a mean for each one of those and then plot them, and that would begin helping you understand the relationship between the state and some other factor that might have a correlation or relationship to the location. And these again are called y bar and x bar, and this is at y sub 1 and x sub 1. And I and j can be any number for if you have 100 samples, I could be anywhere between 1 and 100. And the same way over here on the outcome side, or the response variable, as you'll come to find out, the way it's named inside Minitab. All right. So what I want to do here is I want to go through an example of read auto sales, and this is going to be there's not much data here. I just picked off some Y's and X's, and it's sales versus advertising, I believe. And so you have this auto sale company, and they run TV commercial. What's the name of what was it, Weiler up here?
Jeff Weiler.
Jeff Weiler.
And then Holden Motors is right across from
There you go. Okay. Now, if Weiler, or what's the place across the street? Holman Motors, if one of those two people, okay, one of those two companies pushes some advertising out there, would you expect their sales to go up or down? Up. You would expect it to go up, okay? That's a positive relationship. The more in general, okay, the more sales you have, the more advertising you have theoretically pumped out onto the network or social media or whatever the case might be. Okay, so if your sales went down, what kind of slope would you have? You'd have a negative slope. Correct. Is that good or bad? If you put on more advertising, you get less sales. Yeah, you're wasting money. Okay. Say again. Yes, you might have the wrong messaging out there. You might be, the messaging in Batavia is very different than the messaging in Indian Hill, as an example, as far as what people will respond to. And that's the definition of target market. Is you go after, when you target market, you're going after a group of customers that best respond to your messages, or more importantly, you and what you're offering in the marketplace. So, here's his data set. I think here we go. Come on. There we go. Excellent. So, you have a number of ads, and this is on any given, I think this was any given weekend. And here was the sum of those, and the average number of ads. And this is a Y hat, so we're going. This is a sample. Okay. Is the X bar is equal to 2, and the Y bar is equal to 20. Same old, same old. But now you take that, and you're going to create the slope that best fits those 5 X's and Y's, or data points. Remember the scatter plot we did? That's all we did. We took the X and we took the Y, and we intersected them in the graph. That's all we did. And so now we're going to take those dots, and we're drawing a line that best fits all those dots. And so and then we create the Y-intercept. And the way you get the Y-intercept, as we talked, is here's B sub 0 it's just a mathematical formula. Whatever your Y bar is minus B sub 1, which is your slope, times your X bar, creates your Y-intercept. It's just a mathematical maneuver. So now, if you know that B sub 1, which is your Y-intercept, or is your slope, is 5, and you know that B sub 0, which is your Y-intercept, is 10, and you plug it in the old Y is equal to A plus B mx, A plus mx, what's the formula for that line? That's right. Y is equal to 5x plus 10. And it's the same thing that you've learned from, for 10 years or 15 years or whatever the number is. And the only difference is we're calling this B sub 0 as the Y-intercept and B sub 1 as the slope. So instead of M, we're calling it B sub 1. Instead of A, we're calling it B sub 0. So here's the estimated regression equation, linear regression equation, based upon all these, kind of this manipulation, not manipulation, but the calculations of summing all the x's and the y. And what you're doing is you're finding those spots where the variance or this summing process is minimized. Now, in this course, are we interested in whether you can do this calculation or not? I hereby accept that you guys can do algebra, okay? But so that's why you're sophomores, juniors, and seniors, and so I accept that you can do algebra, you can do mathematical calculations, you can put it into Excel all day long. But what we're going to do is we're going to take these mathematical crunching of numbers, and we're just going to bump it into Minitab. Minitab has all the t-tables. It can crunch numbers faster than any 12 human beings could, and it's going to be accurate most of the time, unless you put something in there that doesn't make any sense. Okay, because I guess everybody's heard the term garbage in, garbage out. GIGO is what they used to call it, and again, it's a little bit of a just an overused expression, I suppose. So now you say, and you come down to y hat. And this is the way it's said, y hat, and this is a hard symbol to make, so if you just put y in there, I'm good. But on the exam, on the exams and quizzes, you'll see the y hat is equal to 10 plus 5x. So you put in any value of x, and this is why it's so wonderful, or in some respects, near to it as, again, that's a little bit of a Schulteism that I talk about, coefficient of determination. But this is equally as powerful, because you can say, okay, if I want to have 10 sales, if I want to have 20 sales, if I want to have 30 sales, all I have to do is plug in the number of ads, and out comes what's going to happen, the outcome variable. Very, very, very powerful. So what I'm going to do here is I'm going to go in and I'm going to run this in Minitab, and then we will also do this on Thursday. So I'm going to demonstrate it here today, and then for Thursday, and I'm not done yet. So, but we might finish up pretty early. Okay, but on Thursday, what we'll do is we'll go to the computer lab, and you'll run Minitab. I've got the steps all set up for you. I'll have you do you'll do one of the exercises, in-class exercises, so you get used to it, and then you can do your case, and you'll actually be able to do your Minitab runs. There should be a little more time than on the first case to do your runs on Thursday. That's the plan anyway. Make sure I'm gonna close this out right. Let's close it.